to this computer. Okay, people. 14.1, 14.2, talk to me. Yes, ma'am.
38.
38 in 14.2. Okay. We want to know if this function is continuous, right?
Or on instead of 1.
Right. So where? So our function is given as piecewise. F of x the fraction is xy over x squared plus xy plus y squared. And that's only when we're away from the point 0, 0. And then it's 0 at the point 0, 0. So if I think about this as a rational function, right? That should work everywhere it's defined. The only place that's undefined is where the denominator is 0. But x squared plus y squared is always bigger than 0. And I can't get xy equals x squared plus y squared. That's not going to work because it's okay. So that the bottom's okay. Because if I think about x squared plus y squared plus xy equals 0, then that's the same as x squared plus y squared equals minus xy, right? But for this to be a positive number, this x and y have to have opposite signs, yes? So I'll only be looking in this quadrant and this quadrant, where x and y have opposite signs. So if I were to look, say, where x and y are equal, right? Then I would have 2x squared equals minus x squared. That doesn't work. If I were to look at where x and y were, well, minus 2x, I don't think I can make this match here. I think the only problem point is going to be 0. So let's look at 0, 0. And really, what I need to show for this function to be continuous, I need to show that the limit is 0. So here's my question. Because if it's continuous, there's a value and the limit as we approach. So did I plug the hole properly, right? So first question is, what's that limit? So if this is true, then we are continuous. Otherwise, we're not continuous.
Okay, so and then when you do the limit,
Yes.
can you like hold on, can you just pick whatever function or like approach? Can you pick whatever approach you want to do?
Yes, you can pick whatever approach you would like.
Just did y equals mx.
Sure. Because in this case, I see, hey, everything on the bottom is x squared, xy, y squared. Those are all quadratic terms. And the top is quadratic as well. I think using y and x having the same power, adding that m in, then let's see what happens. Yeah, I think that's a perfect expression. And if you get something out that depends on m, then the answer is that limit doesn't exist. So you can't plug the hole. You're welcome. More questions. Yes.
For 14.132, we have a massive function with a graph.
Matching the function graph, yes.
I think I know the others, but C and D were just struggles.
Okay. So let me think about C and D. Now, I'm going to do this waving my hands in front of you, but I need you to think about this for a second. I see x squared plus y squared in both of those. So my brain immediately lights up and says, I can do things like this in polar. Let me think about this like it was polar. Ln of x squared plus y, that's r squared, right? So that should look like an ln graph in every radial direction. Oh, so I'm looking for something that kind of looks like a funnel. Cosine of square root of x squared plus y squared. Cosine of r. I should be looking for something that's a cosine, but it doesn't just go in one direction, it goes in every direction. And it's the same height all the way out, cosine of r. So in that case, all of a sudden my brain says, okay, I'm looking for a funnel for C, and I'm looking for a wave like a ripple in a pond, only it doesn't get smaller as it goes out, it stays the same height. Because it's cosine, right? -1 to 1. It should be wiggling like that in every direction, like a rock dropped into a still piece of water. Whenever I see that x squared plus y squared, my brain lights up and says, think round. And now I can go back here and I can say, do I see a funnel? Do I see something that has that ln graph to it? I think I do. Do I see something that's wiggling back and forth? I think I do, no matter what direction I'm taking. Now, the other side of this is that I can also go into my grapher and actually physically graph it. And that would absolutely help. But you see how I did the analysis? I said, okay, wait a minute. What should this graph look like? When I see x squared plus y squared, I think of it as r. Now, we could also take that differently and say, oh, let's do traces, right? ln of x squared plus y squared. If y is 0, that's ln of x squared. So in the place where y is 0, that's the plane. It should look like the ln of x squared. It should also look like that if x is 0, so it should look like that and this in x and y, and then I go back to pictures and try to say, if I cut it, which of those are going to look like that? More, better still?
That makes sense, but I just,
Oh, no, it is not. It is not at all obvious. But remember, long time ago in pre-calc, okay, here's a parabola. Which graph is it? Is it this? Here's the equation. Which of these? We did this way back in Calc 1. We did it in algebra. We did it in all of these different courses. It's kind of like, I'm not used to thinking in 3D. Takes a little pain. It is unquestionably a pain in the neck to switch your headspace around. This is why I like having a 3D grapher. I would draw these and then play with the pictures as well, so that you can say, oh, okay, now I see if I do look at it this way or this way or this way. I'm dating myself. The movie Ender's Game, a couple of years ago, there was a movie about an Orson Scott Card novel about kids who fight a war playing video games. They think they're playing video games, but they're actually playing the directions of the real ships. One of the games in this is a starfield battle, and the hero of the story, Andrew, keeps turning the screen. So he's always looking at this 3D section of space in different directions. He keeps spinning it in 3D to rotate and see, so that he can talk to the people who are in the ships under his command and say, well, if I look at it this way, I see. I think that's the sort of eventual goal for visual intuition. That takes a long while to develop. It really does. And graphing these helps at the beginning. Better. All right. More questions. Ask me more things. Yes.
Can you do 14.220?
20.
Like,
This sucker. I need that over here so I can read it. 1, 2. Okay, 20. Limit x, y, z goes to 0, 0, 0 of xy plus yz over x squared plus y squared plus z squared. Compare that one with the one right above it. I think this is easier than you think it is. Hang on a second. Xy, x squared, x, y, z. These are quadratics, aren't they? Everything here is a squared term. X times y, 2 variables, y times z, 2 variables, x second, y to the second, z to the second. They're all second powers. So what if we played that y equals game here? But I'll need to play it twice. Pick another letter.
And
So now I'm coming in on a straight line, right? And now I can turn what is a 2 variable, 3 variable expression into a 1 variable expression.
you're just supposed to like know to do that?
No, I just took the idea you already did and I said, well, let's take it a step further.
Do it with Z too?
Yeah.
And you can just do that.
Well, again, this is a line whose slope in the y direction is m, and whose slope in the z direction. So I've got a direction vector 1 mn. I'm coming in along a straight line. All I have to do is pick the direction vector. Isn't that weird? It is. It's absolutely lame. It's an insane thing. How would I know to do that? Because I took that slope idea and I said, well, what if we did it in 2 ways?
So those aren't two different lines.
Ah, so really it's one line. Coming in 3 dimensions, right? That, duh. But it's exactly the same. I want to come in on a different straight line. How do I describe a line in 3D? I need a direction vector. So by creating this as my direction vector to go with those, I can do this substitution. Oh, that's sneaky, sneaky, sneaky.
And then so for it not to depend on the slope, you wouldn't be able to have any M's or N's.
Right. When I finish the answer, it should be a number, right? This limit should be like 3 or something. Okay, so wait a minute. We thought about a function of 2 variables as having a surface to it, right? But now I've got a function of 3 variables. So like, my picture's all sorts of effed up in my head. Temperature. At every given point in this room, I could put a thermoprobe right here, a thermostat or a thermocouple probe right here. Say, what's the temperature at this XYZ? What's the temperature at this XYZ? Now, I want you to imagine, this is the hard part. I want you to imagine the picture in the matrix where you see all the green stuff floating down from the ceiling, right? I want you to imagine that every single point in this room has a label on it with the temperature. Color coded. Cold areas are blue and warm areas are red. This whole room would be filled like I was tripped out of my mind with colors, wouldn't it? That's a function of 3 variables. So now you're going to wander some path in the room and you're going to tell me that the color here is a single value. And that would mean that the limit exists. It's 17 or 12 or -3. But if you got something that depends on M and N, then that limit doesn't exist. I don't know how to picture what that looks like in 3D for the limit not to exist like that, because I can't see four-dimensionally, which is really what I need to do here, and that's just not easy. I made the crack last year when I was teaching this course. I said, yeah, I don't do enough hallucinogenic drugs to see in 4 dimensions, so I don't recommend you do it either. One of my faculty members at Pitt, Bard Ehrmantraut, works on neural modeling. And one of the models he was doing was the model of the retina. He was doing vision. And he was studying, you'll love this, retinal neural architecture. So what's the mapping of the nerves in the back of the eyeball? How does that connect to the brain? And he said the easiest way to think about this is to think about how your nerves interpret stimuli. The only thing your nerves in your eyeball know how to interpret things as is light. Your brain says, hey, this nerve went off, must be a light there. This is why when somebody hits you in the face and your nerves get pushed on, they see lights. Close your eye and close both your eyes, but push on one of them lightly, and you can see colors and sparkles. You are literally triggering the back of your brain to think you see lights because you're pushing on the nerves. And he said, and I quote, the other ways to do this other than with physical impact are with hypnagogic neural reactions, which is the things that happen to you right before you're falling asleep. You start to see these same sorts of patterns as you drift off, or you take a lot of hallucinogenic drugs. At this point in the research talk, I asked if there was a lab for this course. No. Anyhow, I met Bart for a club meeting last week, and that's why I was reminded of the story. Anyhow, more questions. Yes.
So for 38 on 4-1, would that graph look like the one from 32 C? That makes sense?
38.
Yeah.
So this one.
Wait. That? Oh no, 48.
48.
Yeah.
This
So
thing.
Yeah, the question 48.
Yeah, it's going to look something very much like 32C, except there's this factor of 4 here, right? So what does that do? This isn't radius anymore, is it?
No.
So let me think about that. Ln of x squared plus 4y squared. Now it actually tells me to use this to do a contour map here, right? So that means I'm going to set this equal to some number. K. Right? And K will be a height. Let's get rid of the Ln. How do you get rid of an Ln?
You take the you take the
I don't want to take, I don't want to do calculus. So algebraically, how do I get rid of an Ln in an equation?
One. We just.
I don't know what you're trying to say. This is the problem. In order to get rid of the Ln, I use an E, right? Okay, so wait a minute. The right-hand side of this is a number, isn't it? E to the K is some number. X squared plus 4y squared equals a number. I know that shape. I know that shape. What shape is that? That's not a circle anymore. If it was x squared plus y squared, it would be a circle. That 4. That changes. What does that do?
Oh, isn't it now let's look.
Except I'm only in 2D, so it's actually just an ellipse. This is at the height K, we're going to have an ellipse instead of a circle. Now, if you really want to be a pain in the ass, you would go, wait a minute, ellipses, aren't they supposed to be equal to 1 on the other side? So you could rearrange this. And then I can rewrite this part like that. Now notice, if you have two numbers on the bottom, the bigger one is the longer axis. Isn't e to the, so that should be e to the k. Isn't e to the k bigger than e to the k over 4? So this is going to be longer in the x direction than it is in the y direction. So instead of stacking up circles like we did in 32, we're going to stack up ovals in that logarithmic pattern.
You just then plug in different values of K.
Sure. And then I can draw all the different ellipses. I can also graph the original equation in 3D using the mat grapher and tell the grapher, hey, put the contours on here so I can see it in 3D. And then I can look at the graph of the ellipses and see if it looks the same way. So yes, it is absolutely possible to just plug in a bunch of K values here and go to town. Notice though that even when K is negative, e to the K is positive. So we always get a real ellipse. Even when it's way down low, it'll be a small ellipse, but it'll still be a physical ellipse. Yeah, so my contour map should be a bunch of ellipses that are longer in the x direction than they are in the y direction, right? And then I will stack these up based on my values for k, and then in 3 dimensions, I'd be able to see that logarithmic piece. It is not always easy to graph ellipses on the calculator, but there is the conic sections sub program. So if you're on your graphing calculator, under the apps, this is what I love about programmable calculators. Right here, it says apps, right? So if you hit that button, number 4 says conics. I want ellipses. And I can give it A and B. So if you pick your K value, you'll know what those two numbers should be, right? So you'll be able to tell me what's A, what's B. H and K are both 0. You can draw the ellipse right here. And that's usually easier than trying to figure out the equation manually. So let's see. H is 0, K is 0. If I used K as 0, then this would be 1, and this would be a quarter. The square root of 1 is 1. The square root of a quarter is a half. Graph. Goes from -1 to 1, from positive 1/2 to negative 1/2. And I can graph more of them and set the window be as I need. Enter on. How do I get out of here? Ah, I hit y equals again. I knew there was a way back. My favorite thing about this program, it's built into my calculator, and it has all of the equations for the conic sections, so I don't have to have them memorized. And it even shows them in the little pictures to know which one goes left, right, and which one goes up, down. So when k equals 0, we got an ellipse that looked like this. And I would label that k equals 0. And then I just make more of them. More questions. Yes, Ben, hit me. 14,228. Okay, if you, there we go, 14,228. So 14,228. So 28 says graph it and then tell me where you think it's discontinuous based on the picture, right? So I'm going to do 27 and I'll show you all the way through the graphic. So 27 is f of xy equals e to the 1 over x minus y. So the first thing I want to do is draw this picture. So open my grapher, 3D graph. Let me share that so that you can see it. Okay. I'm going to create the equation e to the 1 over the quantity x minus y. That's disgusting. But when I look at this, there's my discontinuity right there. It's fine over here. It's fine over here. There's something weird going on right there. And if I look at that, that looks like it's at 45 degrees between the x and the y axis, doesn't it? And if it's at 45 degrees between the x and the y axis, that looks like it's the line y equals x. Okay, that's my assumption based on the picture. Now let me go back to the equation. And when I look at this equation, I say to myself, well, exponentials are continuous everywhere. So it can't be the E part that's the problem. It's got to be the other part that's the problem. So let's look at the other part. 1 over x minus y. Oh, that's undefined. When the bottom is 0, that's the line y equals x, isn't it? And that's exactly the line where we saw things go to hell in a handbasket in the picture. So that picture matches my assumption. This problem line is y equals x here. As a matter of fact, I'm going to add a new object. I'll add a new equation, and I'll just write y equals x. And you see that that plane exactly splits my two pieces. I'll change the color of that one so that I know it looks different. And I can see the plane is where my exponential changes over. How's that, Ben? That work? I'm going to hope so, since I don't get an answer. More questions, people. Ask me more stuff. There's my answer. Thank you.
When I graph 28.
Right.
Just looks.
Nasty, doesn't it? I would print that picture. I would not actually physically sketch it. I would, screenshot that image and then print it. And just stick it in with your homework. Drawing this looks like a nightmare. But you saw how I had to turn it to see what was going on. You're gonna have to spin that in a couple directions to see where is it effed up. But then see if the place where the picture looks messed up matches with what you think should be messed up algebraically. Yeah, I am fully against the idea of drawing all these 3D shapes by hand as much as possible. It makes sense to try and figure out what they look like, and eventually we might be able to build this idea that we get in our heads. But in the long run, it's not worth it. Computers will do that for me. Draw me the picture. More stuff. More stuff. I will stand by my statement, though, that even in 28, I see an x squared and a y squared. Right? My brain says there should be a circle somewhere in that game. And thus, Jack, why I could say, oh, I see x squared plus 4y squared. That's not a circle. That should be some ellipsy thing. I'm thinking back to what we did with all our conic sections and what we did with our circles. And I'm trying to recognize those patterns because I'm going to see them over and over and over. What else you got?
We're hoping one, completely. It asks about the levels of the surface,
Right.
so is that just describing like what it would look like in the XY?
No, because those are level curves, right? This is a function of 3 variables. Right? F of x, y, z. So a level curve was when I set the equation equal to some number. If I set this equal to some number, then I get a level surface. Take a look back on page 898. We have this function. Right? Function of 3 variables, x squared plus y squared plus z squared. If I set that equal to a number, what shape do I get? Except it's just x squared and y squared and z squared, so that's actually a sphere, isn't it? So I could actually say what I've got is different physical spheres for different values of k. The red one in the middle is when k equals 1. The yellow one that's further out is when k equals 4. The blue one that's further out is when k equals 9. So what happens in your case if we set this function that we were given in 68 equal to a number? Do I get an ellipsoid? If I get an ellipsoid, then I should be able to describe what that ellipsoid looks like for different values of k. You don't have to make pictures. You just have to say, oh, I got ellipsoids, and this is where they're long and this is where they're short, kind of like we did on the exam. You don't have to draw it, but describing it is a good help. Now that's an interesting generalization that I wanna run with for a second. If I say, I wanna know where f of x equals a number. We took a horizontal line and intersected it with the graph y equals f of x. I said I wanna know where f of x y equals a number. I took a z and intersected it in 3 dimensions. So really what I'm doing when I write a function of 3 dimensions equals a particular number is I'm intersecting it in 4 dimensions. And as I said earlier, I don't hallucinate well enough to see 4 dimensions. So what I can see is I can see different values in terms of time. I can think of that ellipse getting bigger, or that sphere getting bigger as time goes on, right? So you could say, oh, I've got an ellipsoid, and then I've got another ellipsoid, and then I've got another ellipsoid, and another ellipsoid. If that's what they are, that's perfect. It's weird. A lot of this class is sitting and staring at the walls and going, what does this picture look like? More questions. In order to take it to its extreme absurdity, I could ask if I had a function of 4 variables, I would be intersecting a 5th dimensional idea, 6 variables, 7 variables, right? I have to keep stepping that up. I don't know what they look like anymore. I just describe them in terms that make sense in 1 and 2 and 3 dimensions. So when we talk about an equation in 4 variables, ax plus by plus cz plus dt equals a number, that's a plane. It's just a plane in 4D, and I don't care anymore. It's a linear surface. If it's quadratic in x and y and z and d, then it's an ellipsoid or a hyperboloid or a catenary or a hyperbolic paraboloid. It's one of those in 4 dimensions. I just can't see it. I'll use the same descriptors. I just can't draw the pictures. And so in order to get around that, a lot of geeks put the word hyper in front. So a hyperplane is just a plane in more letters. A hypersphere is just a sphere in more letters. It's a ball. More questions? Pardon me for a second. All right. What else you got for me, people? Yes.
So if you get a value, because you're proving that it's continuous. If you get a value with m in it, doesn't consider its limit doesn't exist,
Which means it's
not continuous.
ta-da.
Oh, I thought it had.
It asked, is it continuous? And if so, where? And so far, the only point where we think there might be a problem is 0, 0. So we think it's continuous everywhere else. Is it continuous at 0, 0? If that limit doesn't exist, it's absolutely not continuous there. Chapter 2, sections 7 and 8. Way back in Calc 1. We said it was easier to figure out where a function wasn't continuous than to figure out where it was. And that's really what we're doing.
You're 37. It's like 38.
So 37. The problem is x squared y squared over, oh, it's x squared y cubed.
That's
2x squared plus y squared. And then it's 1 at 0. So again, Nora, I would say, hey, that upper function is perfectly fine everywhere except 0, right? As long as both x and y are not 0, this is something over something, that's perfectly fine. So the only question point is 0, 0. So my first question is, what's the limit as we go to 0, 0? Now, here's where I need a gut feeling. I need a hunch. Mia, I need you to answer me a question before I actually start this. Do you think it's going to exist or do you think it shouldn't exist? Which should I try?
um. um,
Okay. I agree with you. At this point, it's very hard to know. So my first reaction would be, well, if it doesn't exist, I'm going to try and play the MX game or something like it, right? So I start looking at powers. I got x squared and y squared. Those are the same power. I should do y equals mx. But it's cubed up here, so maybe that might not work. Let's run with it and see what happens. If I try y equals mx, well, then I get the limit as x goes to 0, x squared mx cubed over 2x squared plus mx quantity squared. And now I do the algebra. I get x squared m cubed x cubed. Wait a minute, that's an x to the 5th on the top, right? On the bottom, I get 2x squared plus m squared x squared. I could factor out an x squared on the bottom, couldn't I? And then I could cancel that, but it would only cancel the x squared on top. What happens when x goes to 0? As a matter of fact, no matter what m I picked, that would be 0, wouldn't it? So now my reaction is, okay, maybe this limit does work. If it works, I'm going to try and do it in polar. This is about to be algebraically unpleasant. Because what I need is I need x equals r cosine theta, and I need y equals r sine theta, right? So on top, I'm going to get r squared cosine squared theta, r cubed sine cubed theta. On the bottom, I'm going to get 2r squared cosine squared theta plus r squared sine squared theta. And this limit is now as r is going to 0. Because if I'm going to 0, 0, it doesn't matter what direction I'm coming from, yes? As I'm going towards 0, it doesn't matter what direction I'm coming from, r is getting smaller. But again, I say the same thing. I can factor out this r squared. And when I do that, I'll be able to cancel it with that r squared. But I'm still left with that stupid the r cubed on top, aren't I? So what happens as r goes to 0? Which means that limit we did was right. This does have a limit. This limit is 0. Is my function continuous? We have a limit. The limit. It doesn't match the value that they gave me, because the value they give me is 1. I remember, again, all the way back in chapter 2, when we first started doing continuity, flip, way back in the book, chapter 2, section 5, continuity. We had pictures. Now I'm turning the page twice. Look, here's a place where there's no value. Here's a place where there's no limit. Here's a place where the limit is fine, the value is fine, they just don't match. That's exactly what we just ran into. Hot damn. That's, by the way, is page 115. So now I write, but f of 0, 0 equals 1. So limit xy approaches 0, 0, f of x, y does not equal f of 0, 0. Not continuous. Continuous, I can spell.
If the equation was like x, y, z, how would you put z?
That's a problem I don't know how to do yet. That's why you'll notice none of these are in 3 variables. But what I need is a 3-dimensional version of polar coordinates. We're going to wait a while for that, but there is such a. Yep. Well, I'm going to tell you my favorite part about it is it's much more, to me, intuitive. Because what you could think of is if I'm doing it in 3 dimensions, right? How do you actually physically measure go that way or go that way? We live on a little bitty dot in the middle of a very big universe. We actually use 3D polar coordinates more than we use X, Y, Z coordinates to define positions of stars. So believe it or not, I'm going to use that more often, but not until we get to it in chapter 14, 15, 14. I think we do it in 14. Yeah, we're in chapter 14. That's very easy. Yes. All right. Yes, ma'am. Absolutely. It is possible to say all of the mx pieces work out, but the mx squareds don't work out. It's possible that if I approach on this line and this line, those match, but when I approach on this one, it doesn't. And then when I would see the mx trig, that would fail. Yeah, or I have to get some really good intuition about where things are effed up. And that no, and I'm not going to try and trick you like this. My goal is not to make this impossibly convoluted and difficult. But it is possible to have a limit of 1 in this direction, a limit of 1 in this direction, and a limit of -1 in this direction.
So you can't just stop, like, that's the thing, like, if you get one for both, you can't, you know what I'm saying?
Yeah. That's the problem with doing limits in 3D is that there are really infinitely many directions, and I have to try and look at all of them. And that's not nice. It turns out there are some really nice results that I can prove much later that will show you that all of the nice functions we like to work with only get effed up in exactly the way you think they should. Hey, it's a rational function. It's only going to be weird when the bottom is 0. It's a square root. It's only going to be weird when the thing inside is negative. It's a cosine, a tangent. It's only going to be bad when the bottom is multiples of pi over 2 sort of deal. So it's only going to be the same stuff. There's an entire group of functions called Schlicht functions, as like David von Schlicht in the first part of his last name, Schlicht. There's an entire set of Schlicht functions that demonstrate some of these pathological properties, some of the really weird things. And there's a group called meromorphic functions, many changes. I don't want to do those. We'll save those for another course. I will see you all tomorrow, bright and early. I hope you have a wonderful rest of your day. Thank you, Ben. I'll see you tomorrow, I hope. Feel better.